it's really important to be thinking, especially in the era of synthetic biology, where we use the raw code from 4 billion years of evolution, right? Remember, A, T, C's, and G's power every cell on the planet, whether they're human cells, plant cells, bacterial cells. They all run on the same DNA. Jurassic Park 101, right? Like, they run on chemical compounds that are common, and that's an instruction set. Those are the zeros and ones, as I mentioned, right? That's an instruction set for making new products. And when you can program DNA into cells, like we do at scale at Ginkgo, that instruction set is valuable. So mapping the DNA and RNA of non-human things is like a USGS 2.0. Looking at the deep thermal vents in Yellowstone National Park, or that chameleon whose skin changes color. That's all driven by DNA code in cells. And so I do think that there's a foundational role in kind of the traditional role of government and these kind of creating the conditions where there's potentially market failures for economic growth and expansion. I think we'd really love to see a more substantive focus over time. And certainly I think the team looking at this is very aware of it. As a concept of like mapping the genetic resources, non-human genetic resources of in our case, the United States, and in other cases, the resources of other countries, and giving them the tools to make sure that they are able to create value from those resources, just like we've done with fossil fuels and other mineral resources, but also doing so with the lessons learned of how those goods have been exploited in the past, and trying not to do so in the same way in the future.
What's the case for harnessing biologic processes to do things in new ways? What are the potential benefits?
Yeah, I think so. This is like a really good area to use tangible examples. We have a really big program with Bayer Crop Science, right? Major agricultural company. And the program has many different facets to it, but the core kind of component harkens back to this idea of massive innovation in chemistry leading to then a similar massive innovation in biology. So the way fertilizer is formed today, for those listeners who aren't chemical engineers, right? It's called the Haber-Bosch process. We take and build massive plants, physical manufacturing facilities, and those facilities are essentially structured to burn a ton of natural gas to suck nitrogen out of the atmosphere and turn it into ammonia-based fertilizers. That process, the Haber-Bosch process, is done also by bacteria that live on the roots of peanuts, legumes in general, but use peanuts as an example. So there's little bacteria that live on the roots of peanuts that take nitrogen out of the atmosphere, use their biological process to feed those plants with the nitrogen they need to grow, live, and produce peanuts. And so so then add one other piece to it. The world's staple crops, corn, wheat, rice, they don't have that bacteria that lives naturally on their roots to do that process. So that's where we use all of our chemical engineering, kind of the epitome of chemical engineering, the Haber-Bosch process, where we use that ammonia-based fertilizer to grow those crops. It is also very important we grow those crops because they feed people on this planet. But the project we have with Bayer, which is a challenging project, which is to take the genetic program from the bacteria on peanuts and learn from it, and then reprogram the bacteria that live on corn, wheat, and rice, or reprogram bacteria and related processes, and then form it into seed coating or other application that you can put onto corn, wheat, and rice, and thus replace the need for some or all of the nitrogen-based fertilizer. If one of the major objectives in our next 50 years has to be removing carbon emissions from the atmosphere, removing both current emissions that happen every day and emissions that have already happened, it's these little things that reduce the need for burning natural gas, as an example, to produce fertilizer. I think that's one of my single favorite examples of like what type of massive impact the engineering of biology or the harnessing of biological processes can have.